All right, good morning. How's everyone doing? Yeah. All right, so welcome back. Any questions before we start? Yes. Just a second. All right, yeah. Right.
In what way are you expecting to do some kind of feature extraction before we
Okay.
or can we
Right. Yeah. So for the pre-process part, we don't want you to. Man, it's too loud. We don't want you to change too many things, but there are certain things that need to be done. And I thought in the assignment description, at some place it should say that. If it doesn't, then this is the old one. Assignment 1.pdf. Right, that's one. So in the pre-process, you need to do right. I think you need to do two things. One is, of course, you'll be given a training data set and a test data set, right? The first thing you need to do is you break the training data set into two parts. One is the real training data set and one a validation set. So just, is it already done? Oh, okay. Okay, if it's already done, then one thing that okay, I hope I didn't give you guys the solution then. So this is the pre-process. So essentially the output needs to be aha. I see, this has already been given to you. So that, right, so the only thing that you need to do here is to, okay, but it doesn't say here, right? I think the TA by mistake gave you the part that you're supposed to write. Oh yeah, so the only thing you need to do is the feature selection. So feature selection also is going to be fairly simple. What you will see is that every image is represented as a 784 length vector, right, which is every pixel in that image. But some of the pixels will just take the same value throughout. Because if you remember the images, right, those corner pixels will always be, 0. So for all the images. So you just need to remove those. So it's a very simple Python, just deleting some columns.
so
That's all for this one.
everything with the zero and everything?
Zero or the same value. I think it's just zero. But whatever is constant, because those features will not matter. They're the same for all classes. Later on in the course, we will see more advanced ways of doing this feature selection. But for this one, I think we'll just keep it at this. So it's fairly easy. So I hope everyone understands. You just need to select the important features. But the feature selection is done using a very simple rule that if a feature takes the same value for all the data points that you have, then you just ignore it. All right, so that's the only thing. I think the only thing you'll learn here is how to do that in Python, nothing else. But the benefit that you will have by removing those is that your training will be faster, because suddenly now you'll be looking at a smaller feature space rather than the whole one. All right? You also used to make everyone sort of normalize the data between 0 and 1. But here it doesn't matter because every feature has the same scale. They are all, pixel values, right? So they are all RGB intensities, which are between 0 and 255. So there's no, you won't see any benefit in scaling it. But in many other applications, which we will see actually in second assignment, is that when you have different types of features, normalization will help. So we'll come to that in the later part of the course. This, yeah, yeah. There was one part I used to ask students to do, which was this part, which is splitting the data into validation and test training. But it seems like that's already done here, so you don't have to worry about it anymore. Okay. Another thing you'll see that the TA does is that he divides the values by 255, which is just to bring it between 0 and 1, because these are, every value is a intensity, right? So it's between 0 and 255. So by doing this, he just brings it between 0 and 1. Doesn't make any difference, but just so that the objective, when you do this, you will see why this is done. Any other questions about the project? Okay, very nice. So today we are going to jump to another topic. So if anyone has questions about Vino, I can take that right now. Otherwise, let's jump to the next topic. Okay. All right. So before we jump, I just want to sort of draw the landscape for you. So what we have done so far, right? What we have done so far is looked at some machine learning algorithms which work under certain assumptions, right? And the most critical assumption for every machine learning algorithm is what kind of hypothesis space is it looking in, right? So the problem setting is the same. You have some data, right? And some force of nature, Mother Nature has labeled the data into two classes, yeah? And then you don't know what logic went in the head of Mother Nature to do that labeling, but all you have is one sample of that data, the training data that we call it, and you have to sort of figure out what that process was so that when a new data point comes, you can label it as well. And we've seen some examples. So far we have been operating under three assumptions. One is, of course, what is our hypothesis space? So we have looked at two hypothesis spaces. One is conjunctive hypotheses, one is k-monotone disjunctions. Another assumption that we have made so far is what is our x, right? How do we define our data points? So far we have defined our data points as vector of binary attributes, a vector of binary features, right? Circular, oval, true or false, and so on. And third thing that we have assumed is that our y, the label, is binary as well, 0 or 1. So because of that, the algorithms that we have looked so far are pretty logical, right? So if you made all these assumptions and you have assumed that, another assumption that you've made is that the concept that you're trying to learn is in this H, in the hypothesis space. So then you can come up with some sort of, these are more search algorithms, right? So you know your answer is somewhere and your data is pretty simple, so you do things like conjunction, disjunction, and you go on towards the right answer. But now we want to make it more interesting because in real world, you will not see many practical applications where data is all binary, right? In some cases it might be, especially if you work with things like survey data, right? There you can still work under this assumption and you can apply Vino there, right? So survey data is when you go somewhere, ask people questions, yes or no, you say, hey, do you think Bigfoot exists? And then say, do you think aliens have landed on Earth, so on, and then you want to classify them as nut job or not, right? So that you could still use Vino algorithm there, but in many practical applications, what you will see is that this is a pretty restricted assumption. So now what we want to do is expand that, so relax that. So what we are going to do today is going to relax this assumption, which will say that instead of x being treated as a vector of d binary features, we are going to say that it is a vector of d real values, all right? So this symbol here just denotes the real space, right? So the idea is that each x is defined using d features. Each feature can be between minus infinity and infinity, right? So suddenly things become much more complex, right? So you can no longer count the size of your space. Earlier you could say that in this instance, the number of data points that you can have is 2 power d, but now suddenly you're looking at you could have infinite possibility, right? So this is now what we will work with. So things change because of this assumption, and things become more interesting and more practical. So it's a sort of natural step forward, right? Another thing that we will change later is that so far, even today we'll assume that y can just take 2 values. Then slowly we'll relax it to where y can take many values. So instead of coloring objects into with 2 colors, you can color it with, let's say, 10 colors. Right? So that's what you're going to do in your programming assignment, where each object can take value between 0 and 9 based on what digit it is, right? And then we will take another assumption, we'll relax it further, and we'll say, what if y can take infinite value? So instead of coloring it red or blue, or red, blue, green, what if Mother Nature colors it in different shades of red, right? So then you have to find out what is the right shade for a new object. So that's called regression that we'll look at later. But today we are going to work under this set of assumptions. All right. So the problem setting is that you have data in d-dimensional space, right? So today I'm going to assume, I forgot my stack of sheets, so we're going to work with this today. So today we are going to assume that, let's say, d is 2. That means each of your data object is represented using 2 features. Let's say weight and height of people, right? So that means that we can plot them in a 2-dimensional space, right? So let's say this is x1, the first feature, and x2, the second feature. So you have objects all over the place, right? You can have infinite objects because this space can be divided into infinite parts. But what happens is that there is some force of nature which then takes this and colors some of them positive or red. Let's call them positive and negative, right? So let's say this is positive and these are negative. Then you're given some training data, which is a sample of that. Ooh, should draw it bigger. Right. So some of these are positive, some of these are negative, and then you're trying to figure out how was this happen, how did this happen, so that then you get a new data point, and we don't know its label. You want to find out if it's positive or negative, right? So this is where we will make our first inductive bias here. What we are going to say is that even though there could be any process through which these were labeled, we are going to assume the way they were labeled was that there was a line, straight line, okay, that Mother Nature drew and then called everything on this side positive and everything on that side negative, right? So that is our assumption, okay? Because in reality, it could have been a curve, it could have been anything, right? It could have been a bunch of circles or any other way to color them. But we are going to assume that the way they are colored is by first drawing a line and then calling everything on this side positive, everything on that side negative. Which means that the job of our algorithm is now a little easier. It is a little easier because now we have to figure out what is that line. And once we figure out that line, then given a new data point, we can apply that test. That is it on that side or this side, and make our prediction, right? So we saw this in last class as well. We are going to denote the equation of our line as this. W transpose X is equal to some B, right? So that's a standard way of a theta. I use theta here. W transpose X is equal to theta, right? So W transpose X is just a mathematical notation for dot product, which essentially means W1x1 plus W2x2 is equal to theta. So that's the equation of this line, right? So of course, so essentially this W is a weight vector. We call it a weight vector, which has 2 entries, W1 and W2 transpose, right? We always denote vectors as column matrices with 1 column. That's our notation. So this is sort of our weight vector that we want to learn, and also the theta. So these are the parameters of our algorithm that we want, or the line that we want to find out from the training data, all right? And the one thing you will note here is that even our hypothesis space, right, has suddenly become infinite, of size infinite, right? Because these can take any value, right? So now we are no longer looking at, like in conjunctive hypothesis space, we had 3 power d plus 1 possible hypotheses we had to search there, right? But now that's no longer the case. We have to search, because the line could be anything, this, anywhere. So we have to search the right line, right? So suddenly the problem becomes more interesting. We are no longer looking for a straight line. Oh, sorry, we are no longer searching in a finite space hypothesis space, finite size hypothesis space, but we are searching in an infinite hypothesis space. So even though we have made a very restrictive inductive bias, right? We are saying that the data is separated by a line and we want to learn that line. But even then, our space is still size infinity. But what you'll see is that it still makes it a little easier to learn the right answer. Any questions so far? Okay. So now we'll look at one algorithm that does that. It's called Perceptron. All right. So Perceptron is inspired by how brain works. Okay. So people who study brain know that a brain essentially is made up of small computing units called neurons, right? And the idea behind the neurons is that they are kind of like small computers, but what they do is they take input from outside, they combine it and create an output, a signal that we also call activation. And that signal goes to different parts of our body and, makes us respond to that stimulus, right? So perceptrons, and then we'll also look at neural networks, they're all sort of inspired by that, right? Of course, in human brain, there are many neurons, and they are all connected to each other. So it's not as simple a problem as what we will see in perceptron, but it's kind of inspired with that, right? So don't think that if you know a perceptron or if you even have a neural network, then you can create a machine that can operate like a brain, because brain's complexity is, magnitudes higher than what these things can do. But the atomic unit is the same. There is a notion of some input coming in and then something going out. So input and output, right? So that is what a perceptron mimics. Okay. So there are two ways to look at a perceptron. One is from more of this brain kind of neuron, and one is more geometric. So let's first look at how it looks like if we want to look at it as a neuron, right? So the idea behind a perceptron is that it's kind of like a box, right? So let's say I draw a box around here. So what it takes is some inputs. So these are the different features of the example, right? And then inside the box, so think of it like a box with wires going in, and just inside, for every wire, there is a sort of a coupler which multiplies some weight with that input, right? So each input is like a small current going inside with different intensities depending on the value of this feature and every feature, and that gets multiplied with some weight, and then it goes into sort of this aggregator which takes all of these and sums it up, right? And then at the end, so that produces this output, which is this, right? Which we also write as W transpose X. So I can write this entire vector of weights as my W and all of these inputs as X, right? So all this is, all this is doing a W transpose X, or an inner product. And at the end, there is a sort of this thresholding unit. What that does is it looks at the output coming out of this aggregator, which is W transpose X, and then it applies a threshold to that, which we also call the bias. So if this value is greater than theta, then the output will be +1. And if it is less than theta, output will be -1 or 0, right? So you can do anything, but basically it's a binary output which is used. So this perceptron is also called a thresholded perceptron, because it's doing the activation and then it is performing a thresholding test and then giving you a binary output, which we want, right? Because at the end we want a binary output. Is this belongs to the concept or doesn't belong to the concept, right? There are also, and later we will also see a variant of this, which is an unthresholded perceptron in which there is no activation function. There is no thresholding. All you get is a real number out as an output. Okay. Any questions so far? So now what we are going to do is figure out how to learn these weights, because we don't know what these weights are, right? If you knew these weights, then applying this forward process is very easy. Just feed the input in. But the task is, given bunch of these examples and corresponding labels, how do we learn the inside of this perceptron, right? So that's the training part that we're going to look at. Another way to look at perceptron is just as we said earlier, right? So all we are trying to do is trying to learn the equation of this line, right? So W transpose X equal to theta. And the idea is that given some data, right, this is positive, this is negative, we try to learn the equation of our line such that anything on this side of the line will be positive and everything on other side will be negative, right? So both are doing the same thing. We are going to study perceptrons like this, but their actual geometric effect is this, right? Any questions so far? All right. Now comes a very interesting part, and I want you to really try to understand this, which is the notion of a bias. So I'm going to talk about something called bias, but this is not the bias that we have looked at so far, which is sort of the inductive bias, but this is a bias more from a geometry sense, right? So let's think of this line, W transpose X equal to 0, right? What do we know about this line? Essentially what this line means is that W1x1 plus W2x2 is equal to 0, right? One thing we know about this line is that the slope of this line, of course, will be determined by what W1 and W2 are, but one thing that will determine, one thing which is constant is that it will always pass through origin, right? For any value of W1, W2, it will always pass through origin. Now, that is not good for our learning. We cannot assume this, because what if our data looks like this, right? Plus, 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 plus here, and then minus, 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 minus here, right? If we try to learn lines like this, then it will always go through this. So we might not be able to draw a good line, even though there is a line that can be learned, right? Which means that we need to assume that there is a bias in the data, which means that the equation of the line is actually this. Then we can draw the line like that, right? So there is this notion of bias that we need to have. So we can't, and this will become more clear when we look at neural networks too. But in general, this is something that we do in statistics as well, is always introduce a bias term, because that, or intercept term, so that ensures that the line doesn't necessarily have to go through the origin, right? It makes it more expressive. Okay, so that's the notion of that. One way to learn the bias is, of course, so you can treat all of these three things as our unknowns, right? But one more easier way to do it is that we assume that there is a third dimension. Okay, so we add one more dimension to the data, to X, but we assume that that third dimension always takes the value 1. So it's a constant dimension. So instead of writing x1, x2 as my data point, I will say my data point is x1, x2, 1. So instead of this being in R to the 2, this will be in R3. Okay? And then the reason we are doing that is then we can write the equation of our line as W transpose X equal to 0. Okay, but remember, this X is not our original X, but this augmented X, right? So which means that our W will also have three terms. It will have W1, W2, and another one, W0, right? This will be the bias term. So if you just try to understand the equations, this is W0 is equivalent to minus of theta, right? Because theta, if you bring it here, that's having the same effect. Now you might wonder why am I doing this? The reason I'm doing this is because then I eliminate writing out one extra term. Everything gets folded into the W itself. So it becomes a little easier to sort of work with, right? But you could maybe you're too strict. You say, I don't want to add this term. I'll keep this theta. And you can still work with that. But for our sort of discourse, in this course, we will assume that that bias term has been folded into the data itself. So essentially, then what we are going to do is that instead of trying to learn a line in two-dimensional space, if your data is in 2 dimensions, we are going to learn a plane in 3 dimensions, right? But that plane will always go through the origin, because we are going to learn an equation like this. Okay, so it's a sort of it's a notation trick, something that we are doing to just make us write fewer notations. So then we can just express our linear model or our perceptron as this. So then our perceptron also changes a little bit. So essentially what that means is that you have, all of your inputs going in, x1 and x2. You had this w1, you had w2. They were bringing things here into this aggregator, and then there was a thresholding unit. All you do now is that you assume that there is another input going in, but the input to this is always 1, and this is w0. Right, so it just makes it a little nicer to work with. Any questions so far about the bias? So this is something that's easy to understand, but that's something that you always have to be careful about, right? Do not ignore the bias term. And another thing is that you can add the one here, you can add the one in the front, you can add the one in the middle, doesn't matter. Only thing you need to remember is that the corresponding weight that you will learn will also be in that location, right? So typically we add it in the front, even though I gave you example where I added in the end, but typically we add it right in the front, just for consistency. Any questions so far? All right, so now let's look at the algorithm that we want to understand. So the algorithm that we are going to look at, so what we have done now is we have added the bias, so we have removed that theta term altogether. So all we want to learn now is an equation of a line which is W transpose X is equal to 0, right? So this is our hypothesis space now. Our hypothesis space consists of all lines or planes, all linear hyperplanes in that d plus 1 dimensional space that go through origin. And we want to learn the one that separates our data into plus and minus, right? So it is still an infinite dimensional space, but at least we know that they are all lines, right? So that has made you will see that makes our job a little easier. So we also call in machine learning that hypothesis that we will learn eventually as our decision surface or decision boundary, because we are going to use that to make our decision, right? So later on you might hear me use the term decision surface or decision boundary. Okay, so how do we train this? So given some training data, how do we learn that weight vector? That's the question, right? So there is one algorithm called perceptron learning, which we will employ, which is fairly easy to understand. So it's kind of very much like Vino, but slightly different. So let's go through it, right? So the idea is that you start with all zeros in your weight vector. So you assume that your weight vector has all zeros, that's the initialization. Then you start looking at one training example at a time. So you get the first or ith training example. The first thing you do is you predict, you see where it lies with respect to this plane, and you use that to make your prediction. So if it is greater than 0, you say that this object is +1, and if it is less than 0, you call it -1. All right? Then what you do is you check if you have made a mistake or not. So remember, the C star xi is the true label. So if you have made a mistake, you add something to this weight vector, okay? And this is where you need to brush up or just go back to your days when you were studying Euclidean geometry, right? So if you have a line, right, which is specified using W, if you add something to W, right, all you're doing is you are shifting, you are rotating it, right? You're assuming that it is going through the origin because you've added the bias. So when you add something to that W, all you're doing is you're going to rotate it a little bit, okay? So the idea here is that you start with some weight and then you keep rotating that weight vector as you make mistakes. And every time the reason you rotate it in this way is because this will ensure, this is also called the perceptron learning rule, this will ensure that now the new weight vector is going to call this object as the right class. Okay, so if it was calling it negative when it was positive, your weight vector will rotate a little bit so that now it falls on the right side, and then so on until it sort of until you're done with the training data. Okay, so that is just a very simple perceptron learning algorithm, very similar to Winnow, except that the update rule is slightly different. Okay, any questions so far? We're going to look at an example. Okay, all right, all right. So let's see. Oh yeah, we can look at here. No. Okay, I had a notebook that I can show you. All right. So this is called Perceptron demo. Somebody asked me how to get to these notebooks. These are available on our course web page. So if you go there, right, for every section that I teach, I have notebooks. So right now we are doing part 4. So if you go to part 4 notebook, that will take you to Perceptron demo. And then you can download it and run it on your end, or you can just see what's going on here. All right. But okay, so let me go here. So this is just a demo of how this algorithm works. So what I'm going to do is I'm going to first generate some data. Okay. Now data generation also is another area itself, but so you don't have to worry about it right now. I think once we sort of try to look at how about random variables and statistical distributions, you will understand it more. But the basic idea behind this whole bunch of code or this cell is that it's trying to generate the data that we have seen, right? Some positive, some negative. I want to ensure that there's a line in the middle. So this is how the data looks like. Sorry. So here I've also made an assumption that all of your data points, they are defined in two-dimensional space, but I've also ensured that they all lie on a unit circle. This is just to make it slightly easier to work with, because if it is on a unit circle, then I can assume that the line that I draw will go through the center, through the origin. Otherwise, what will happen is I'll have to look at three-dimensional space because I have to add the bias and so on, right? So that is, I mean, it is a restrictive assumption, but you still can have infinite number of data points, right? Because you can pick data points from anywhere on this circle, right? So that's just one assumption that I've made for this example. But all I've done is I've created a bunch of data points and I've given them some label, right? And what you will see is, because of the way I wrote the code, is that you can draw a line through this such that all the blue ones are separated from the red ones, okay? So I think the red ones are called the positive class. Yeah, one of them is a positive, one is a negative, right? So now the perceptron, now what we will do is we'll apply the perceptron learning algorithm on this and see if it can learn that line, right? So this next code is essentially the perceptron learning algorithm. So I mean, you don't have to look at it right now, but later when you go back, you can check it out. A lot of this code is just for the plotting. The real perceptron learning happens around here. So what you do is you say my weight vector, which is just there are two weight entries because your data is two-dimensional, and we have already incorporated the bias here. So the weight we initialize it to 0, 0, right? And then I go through every data point. And I look at, the first thing I do is I make my prediction, right? That's the first step. And then I check if my prediction is same as my output, right? Or my true class. So here we are assume that true class is -1 or +1. So this is another way to check if it is same, right? So if I predict something as +1 and the thing is also +1, then it will be positive. But if I predict it's positive, it is negative, then it will be negative, right? So if this is less than 0, that means I've made a mistake. So I update my W. So this is exactly like what that code says. And that's it, right? And you keep doing that until the data is done. So if I run this, you will see sort of an animation which will show you how it goes through. Let's run it. So you will see that slowly, so let me run it through once. Right, so the arrow kind of denotes what is my training data point at this iteration, and that blue line is our hypothesis, right? And what you'll see is that it has already converged. So it's not moving anymore because it's not making any more mistakes. So you see this is already a good line. right? So that is how the perceptron learning works. Any questions? Yes. Right. Right, so good question. The question is, what happens if there is a positive value between two negative values, right? So the answer to that is that if you're assuming that there is a line that separates the two types of points, then that scenario will never happen, right? Because what perceptron learning algorithm, the assumption that it works with is that there is a line that separates the two types of points. So if there is a line, it will learn it. But in 5 minutes, I will show you how to learn even when that there is no line like that. All right. So just hold that thought, and we'll come to that. Okay. So this is basically a demo of how this whole thing works. Very good. But the question is, does it converge, right? And the answer to that, if the data is linearly separable. So when I say that, what I'm saying is that if my hypothesis is correct, that means my target concept does lie in the concepts or hypothesis space of all lines, then this algorithm will learn it, as long as it gets enough data, of course. But if that is not true, then it will never learn it. So take a look at this example, right? So this is what we call an XOR example. So there are two negative points and there are two positive points, right? So that's kind of like what you said. You can never draw a line that can split it in two parts, right? There's no way. So if your data is like this, then perceptron will not converge, okay? And in general, so how do you know if I give you two bunch of points, and so how do you figure out if you can draw a line through that or not? So geometrically, it's pretty easy, right? So all you need is a bunch of pins and elastic bands, right? So if you have data like this, so these are all my positive examples, and these are my negative examples. You stick pins on each one of these points and try to draw a convex hull around them, right? If you try to stretch a elastic band around the outside points for both classes. Oh, I'm sorry. It's clear for me. Okay, that's fine. I'll keep it zoomed. But yeah, so if you can draw convex hulls up around your two sets of points, if they intersect, that means you cannot draw a line, right? So if that happens, then perceptron will not converge, essentially, right? So that is the point. Any questions? Follow up? Okay. So in fact, people have done a lot of research, theoretical analysis of understanding how perceptron converges, right? So again, go back to our previous discussion about number of mistakes, right? So people have done research on how many mistakes will perceptron commit before it learns the right line. And of course, all those convergence proofs work under certain assumptions. Assumption number one is, of course, that there has to be a line, right? If there is no line that can separate the two, then it won't converge. But if there is a line, then there is another assumption that you make, is that there shouldn't be any error in the data. The other thing is, of course, we assume data lies on a circle. This is just to make the analysis possible. Otherwise, it's very hard to analyze these. And another thing is that we also assume that there is some positive gap between the positive and negative examples. So the idea is, so if you go back to this, right, what it says is that it shouldn't be that this blue and this red are like very close to each other. If that happens, then it will take longer to sort of learn the line. But if there's a clear separation, then you can learn a line more easily. So essentially what you will see is that this distance, right, the minimum distance between the red and any pair of red and blue points is what we define as delta. And what people have shown is that the number of mistakes that perceptron will make is a function of that. So if the separation is very large, then you will make fewer mistakes. But if the separation is very small, then you will make a lot of mistakes. This book by Marvin Minsky, it's called Perceptrons. So Marvin Minsky, of course, famous AI researcher from MIT, he wrote this book called Perceptrons, and he did all of this convergence proofs in that, where he showed that the number of mistakes you will make is proportional to how separable your two types of points are. If they're very close, then you will make a lot of mistakes. And this actually spelled the sort of the death of perceptrons, because basically people said that it, even though it's a nice algorithm, it makes too many mistakes, right? But there are proofs all out there. The proofs are not part of this course, but if you're interested, we can talk outside about it. All right? Any questions before we step forward? Perceptron. All right. So the next thing we're going to do is look at taking the next step, which you had pointed out, is see, so far what we have assumed that there is a line that is there that we want to learn. Perceptron will do that. But what if we cancel that? Like, what if there is no line, but we still want to learn the line? That's this expression, that your target concept does not lie in the hypothesis space. But can we learn a line? So what does it mean to learn a line there, right? So the idea there is that there are two ways to do that. One is we can say that, hey, instead of learning lines, because we know that the concept is not a line, let's try to look at curves and polynomials and so on. That's one approach, and we will do that later on, but that makes things more complicated. Another approach is, what if we can learn a line which is good enough, which might not perfectly separate the two types of points, but it does the best it could, right? And that's also known as the principle of good enough, right? Don't try to get the best answer, but try to get the good enough answer that is good enough under the present circumstance, right? So that is the notion that we're going to look now. And in fact, that is going to be our guiding principle from now on. From now on, since things have become so complicated, we are no longer going to learn the best answer, right? Instead, we are going to learn the best possible answer, the principle of good enough. It also works very well in real life too, right? Principle of good enough. Okay, so now let's look at how we do that. So it turns out that there is an algorithm. It's called, we'll still call it perceptron learning, where we can learn the best possible line. So what is the best possible line? The first thing is we need to define that, right? So let's do that. Okay. So for example, let's look at this data set, right? And I'll tell you that this data set is not linearly separable, because if I stretched two elastic bands, they would overlap, right? So, but how about this line? This is a pretty good line, right? Because it's calling most of the red points red, most of the blue points blue, maybe making mistake on one, right? So that's maybe a possible good answer. But there could be other answers as well, right? There could be another answer which would go like this, that would make 3 mistakes, something would make 4 mistakes, and so on. So we want to figure out the line that would make the minimum number of mistakes. So that is the idea. So the idea is which hyperplane to use, right? Which one to choose. And the way we are going to learn that is by posing the problem no longer as a search problem. Now we are going to pose it as an optimization problem. We are going to define an objective function, okay, which kind of translates to how many errors we make. And then we are going to solve for the unknown, which is the W, which will optimize or minimize our objective function, right? And we will use this over and over again in the entire course. Later we'll look at probabilistic methods, where instead of minimizing the error, we are going to maximize our likelihood or prior or posterior probability. So it's all the same philosophy. Instead of trying to search for the best answer, we're going to say, here is how we define the quality of my solution, and let's try to find the unknowns by optimizing over it, right? So the questions that we need to understand are, what is that objective function that we have to define? And then what is the optimization procedure that we're going to employ to learn that, right? Any questions so far? Okay, let's carry on. All right. So now what we're going to change is we are going to change the perceptron a little bit, and I'll tell you why. So this is a perceptron, of course, the same as I showed earlier, except more pretty colors. So there is an input layer which has all our weights, W1, W2, all the way down. We are going to assume that we have already added the bias term here. So these are our inputs, and this is where the aggregation happens. For now, for the perceptron training in this setting, we are going to assume that this is an unthresholded perceptron, okay? Because and I'll tell you why. But let's just bear with me. So for now, we are not going to apply that threshold that if it is greater than 0, then output is 1, otherwise -1. We'll just take the raw output, which is W transpose X. Okay. So we are going to define our error like this. Okay. Our error is basically the difference between what comes out of the perceptron, which is W transpose X, and what is the true label. Now remember, we are assuming that our true label is either 1 or -1. Okay. So the idea is that if your W is good, right, then for every positive example, this value will be towards 1. And if your true label is negative, this value will be towards -1. Yeah? Is that 1 or -1 or? This is something I always confuse myself with. I think it's true, right? So it's +1 or -1. So you define this as our error function. Okay. So you take any W. Here is a basket of all W's. I just pick one, and I can measure this error, right? So one way to do this, to find the best W, is just pick every W from this basket, compute this error function, which we also call objective function, and find the one that is giving me the least value. And that will be the best answer. That will be the answer like this, right? Of course, as I said earlier, this basket is of size infinity. So I can't just keep picking things from here. We need a more principled way of searching through these W's to find the right answer. And the way to do that is by posing this as an optimization problem. Well, actually, we have already posed it as an optimization problem, right? So we have defined an objective function. And the idea, this is unknown. We don't know what this W is, but rest of these things are known. We know what Y's are and what X are. Can we find the W that minimizes this, right? The minimization process. So I'm assuming all of you are familiar with how mathematical optimization works, but I'll give you a quick sort of a intro to that, and then next class we'll go into the actual algorithm, right? So what you will see from now on is that most of machine learning algorithms are based on optimization. All they do is they define some objective function, try to find the unknowns by optimizing them, right? And the idea is how can we do it fast enough and more accurate and so on, right? But the general optimization formulation, of course, if you go back to your any math course, is that you have some function f0 of W, and you're trying to find the W that minimizes this. And a lot of times you also have some constraints on the solution as well, right? Which we define as some other functions. But in the case of Perceptron, there are no constraints. It's an unconstrained optimization problem, very easy, right? There are many ways to do optimization, right? Because depending on what the function is and what the constraints are, you have to, it's not like there is one method, right? So your methods which are sort of that talk about, they just go search. So they're genetic algorithms, simulated annealing, and so on. There are some that kind of exploit the structure of the optimization problem. So that's the ones that we're going to look today. So there's one particular class of functions which assume a class of optimization approaches, which assume that the function has a certain shape. Okay, essentially they assume convexity of a function. Okay, the idea behind convexity is that the function is smooth. Well, that's other constraints. This function needs to be smooth, which means, or it shouldn't have breaks in the middle. It shouldn't have undefined values for certain values of x. So if that is true, and if the function is nice and convex, which means that there's only one peak or only one, trough, right? Then you can apply some mathematical optimization problems to learn the objective function, or learn the optimal solution. All right, so we are going to assume that our function is convex, and then we are going to find out the right answer, right? So of course, we're out of time. All right, any questions so far? All right, so next class what we're going to do is going to go a little bit more into optimization, but not too much. I'm going to assume that you are familiar with that. So between now and Friday, if you can brush up on some of those concepts, maybe look at these slides so that we can quickly jump to how perceptron training works, and then we are going to move to neural networks. Okay?